But the chapter 5 and 6, we're going to run in tandem, because what they do is they introduce one way to do it, and then in chapter 6 we see another way to do basically the same thing. And so that's why these handouts are a little bit different. So Jenna made these, and so that was really nice of her, because just kind of doing the mashup, I was like, I don't have time to make these. So so Jenna made these, which is really nice. And that's why it's a little bit weird that we're gonna do kind of 5.1, 6.1 at the same time. We're gonna do 5.2 and 6.2 at the same time. And then we'll do 5.3 and 6.4, because again, there's overlap in each of those sections. So we'll see those concepts, how to do it one way and then the other way. And we'll just kind of go from there. But first, we're gonna finish chapter 4. So what we were talking about earlier, right, is if we can't have school anymore, we'll still have classes, right? They'll just be in Zoom. So make sure that you know how to join Zoom and stuff for the online meetings. But so the lectures will be fine, but tests are a problem, right? And so I'm meeting with the other pre-calculus teachers today or tomorrow or whatever. We've got crazy emails going back and forth, being like, what are we supposed to do? Right? And so, because our test wasn't supposed to be until not next week, but the following week, right? And so if we're closed before then that's going to be hard to do, right? So one thing that I would want to do is push the test to next week, probably Friday for us, right? That might still be too late, I don't know. But so just be prepared for that test to be pushed forward a little bit. Of course, it would only be on the material that we've covered up until that point, right? And so so I'll let you guys know once we kind of figure out a plan. It's hard because we don't actually know if school is even closing, right? So it's kind of hard to figure out. Of course, if school's open, then everything just kind of keeps going. But if we have to close, then I'll let you know about the tests and see. We might do, so just so you're prepared, right? I might set up a test on WebAssign for your final exam, for example, where it'll just be open for 3 hours. And I totally understand that, you'll have all your resources and you'll have everything available. So it'll be a little bit different, but at least, if it's timed, then there's only kind of, you have to know some of it at least, right? And so, so that's what we might end up having to do, but I guess we'll see.
Will we get a review package this weekend or something?
Yeah, I'm heading into a very busy weekend because I thought I'd have a little bit of time, but no, I'll get you guys that review package just like last time, right? And I'll post those solutions and everything. And so depending on where we get to, right, if we do bump the test, I'll let you guys know which sections, won't be on it, so you don't have to worry about those. But what's nice is if everything goes as planned, right, then after test 2, you'll have seen everything on the final except for one small question and one larger question. So that's kind of nice, right, to have that under your belt and to have seen it already. So that's kind of exciting, is if we get to keep going as we're supposed to, then you'll have seen a lot of the final already. And that's why I'm happy if we are able to just kind of do test 2 one way or another and just kind of get it done. But yeah, any other questions about all this? I'll just kind of figure it out as we go. We're kind of lucky that we don't know what to do, right? Because if we knew what to do, it means it's happened before. So we're kind of lucky in that way. Okay, I cannot really remember where we ended, but we were in 4.5, and I think we had done solving some of these exponential questions, and we were moving into logarithmic equations, but just for review, do you guys remember which questions from 11 to 38 that we had done? So I pick one that we haven't done.
We did 36, 38.
Nice. Cool. So what if I do 34 to stay with the evens? So what we're doing is we're solving exponential and logarithmic equations, but in this case, we're just solving exponential equations. And we're doing number 34. So 34 has 10 to the power of 1 minus x is equal to 6 to the power of x. Yeah. So what we said when we're solving exponential equations is we want to get kind of the exponential function, this one and this one, on their own, right? And so if you've got one exponential function, then you keep that on this side and then everything else on the other side, right? So we say that we're isolating the exponential function. So if you look at those steps, right, you isolate the exponential function to get it on its own. And then what we do is we take the log, and I'm always going to use the natural log. You don't have to, but you have to use the same log base for each side, so for both sides. So I always just use the natural log. So here I'll just say isolate exponential. There's no way that I could kind of move one over because they're different bases, so I can't combine them even, right? And then the next step is to take the natural log ln of both sides. So what we do, we take the natural log, and remember I write it kind of squiggly, ln of 10 to the 1 minus x is the ln of 6 to the x. Remember, the most important property of logs is that even if we bring this down in front and this down in front, that's going to be equivalent, right? So x times the natural log of 6 is the same as the natural log of 6 to the power of x. And so that's just a really useful property of logs. And that goes for any log. So now I can rewrite this as 1 minus x times the natural log of 10, which is just going to be a number that we can calculate on our calculator, which is x times the natural log of 6. So here on the side, I'll say bring powers down. Now x is on that level playing field that we know how to deal with it, right? So now it's just going to be some placeholder for a number. Sorry. I'm going to break out the 1 minus x, expand it a little bit, right? And so I get the natural log of 10 minus x times the natural log of 10 is x times the natural log of 6. Maybe I have it. All of a sudden, well, you know, when you hear about symptoms and stuff, you're like, it's like, I feel that way. Yeah, for sure. I'm like, oh, my throat.
I've been trying so hard not to sneeze for the past 5 minutes.
It's impossible, right? As soon as you hear symptoms, you're like, exactly. Yeah, it's so annoying. Anyways, I think my throat is just dry. Don't worry, guys. Or maybe do worry. I don't know. But if we're trying to solve for x, right, now we're one step closer. What I'm going to do is, because I like adding rather than subtracting, I'm going to add x log 10 to the right-hand side to try to get the x's on one side and everything else on another side. So then what I get is the natural log of 10 is x times the natural log of 6. Notice that we don't actually need those brackets. Plus x times the log of 10. I can pull out the x's, the common x's on the right-hand side, so I get x times the log of 6 plus the log of 10. And on this side, on the left-hand side, we've got the log of 10. We can just calculate these on our calculator, right? Or if you wanted to, because we're adding, right? The log laws say that if you're adding, then you can take the natural log of 6 times 10, right? That's how it behaves. So that's why it's really important that we know all these log laws, because we need to be able to move things around to make things easier. And we can just confirm that that's the same as the natural log of 6 times 10. So on our calculator, first thing I'm going to do is I'm going to calculate this. So you should have an ln button of 6 plus the ln of 10. I get 4.094344562. And then if I do the ln of 60, right, you should get the same thing, 4.094344562. Either way, right, it's just going to be a number. So even though it doesn't really look like a number, it's just a number, right? It's essentially a placeholder for a number. And so what we do to solve for x, right, and I always like to have what I'm solving for on the left-hand side. So in my mind, what I'm doing is I'm just revolving this around the equal sign. And so, but I know that that throws people off a lot of the time when I do that, because I like to have x equals whatever. And so here I've got x is the natural log of 10 divided by the natural log of 60 I'll use. We want to use all your decimal places, right? So if we do the natural log of 10, you can just do divided by the natural log of 60. And I get x is, and this is a decimal, so it's approximately equal to 0.56238185558. Okay. This here, log 10 over log 60, that's your exact answer, right? Even though it doesn't look like an answer, that's the exact answer. So here, exact answer. And then here, this is your approximate answer. Let's see here. What's another one that we could do? Let's do 28 just for some more practice. I know we're moving into the kind of easier numbers, but it's a different type, sort of. So what we have is we've got 2 times 5 plus 3 to the power of x plus 1 equals 100. If we're trying to solve for x here, we are, x is up in the power, so I know I'm going to have to take logs, right? But to do that, I need to isolate this thing. So that means that I'm going to slowly move things over to the other side, right, to try to isolate 3 to the power of x plus 1. And so here, first thing we're going to do is we're going to isolate 3 to the x plus 1. So we've got, just writing out our formula here, 2 times 5 plus 3x to the plus 1 is 100. Slowly moving things over, right? If I'm trying to isolate 3x plus 1, I'm not going to expand that 2 inside because you'd have to just divide it out again, right? So you may as well just do it from here. And so what we get is 5 plus 3x to the power, or 3 to the power of x plus 1 is 100 divided by 2, which is just 50. Moving that 5 over to the right-hand side, right, we subtract 5 from both sides, so we get 3x plus 1 is 50 minus 5, which is 45. All right. So now I've got my 3x plus 1 isolated. Now I can take the log, and now I can bring that x plus 1 down in front. And so now take logs, take ln of both sides. So we get the natural log of 3 to the power of x plus 1 is the natural log of 45, which is the same as x plus 1 times the natural log of 3, which is the natural log of 45. The natural log of 3 is just a number, right? So I can divide it over to the right-hand side. And so then I get x plus 1 is, and I'll move it to the next page, I think. I get x plus 1 is the natural log of 45 divided by the natural log of 3. Which is just going to be a number, right? But if I'm solving for x, I'm not solving for x plus 1, I'm solving for x. So what I'm going to do is I'm going to have x is the natural log of 45 minus the natural log of 3, or sorry, divided by the natural log of 3, and then minus 1 after that, right? Make sure you subtract 1 from that whole number, right? So not just the natural log of 45. So what we get, right, this would be your exact answer, right? And then we can approximate that with the natural log of 45 divided by the natural log of 3 minus 1. I get x is roughly 2.4649735521. So what you'll find is for testing purposes, everything that we've learned in the earlier sections of chapter 4, we're applying in section 4.5, right? So focus on these problems before I get that practice document to you, right? Just focus on these problems in section 4.5, because they're where we kind of bring everything together, right? And so just focus on doing these and then refer back to the older sections, earlier sections, if there's something that's not clear, but that'll be good. Yeah. We said, okay, there is the exponential equations of quadratic type. I'm not going to do that. We're not going to need it for the test. It's just an extra thing that we could do. And kind of doing substitutions like that is good to practice, but we'll save it for calculus. How about? I think we started talking about solving logarithmic equations, but we didn't actually do one. We did one. Which one did we do? 66. Look at us go. Wow, nice. Okay. So then I guess I'll end the review there. That wasn't, I guess it was review. We'd done it. but now we've seen it quite a bit, right? And so if we're solving logarithmic equations, right? The same idea applies. We want to isolate the logs, which means we might have to use log laws to combine things. Okay. So we might have to use log laws to combine things, to isolate that log. But then what we do is we just kind of reverse it, right? We raise the base of the log, use that as our base in our exponent, and then things kind of cancel out. And so let's do another example. In fact, let's do something kind of, we'll start a little bit easier. Let's do 56. Just kind of quick and dirty. The natural log of 2 plus x is 1. I've already isolated my log, right, on one side. And so now what I do is I raise it. So remember that the natural log is actually log base e. Right? So that's what you're going to raise both sides to. So what that looks like is e to the natural log of 2 plus x. Oops, sorry, 2 plus x is e to the power of 1. How these behave is that e to the natural log of something just kind of dissolves, right? You can think of it as just kind of disappearing. And so what happens is that the 2 plus x drops down and it just becomes e to the power of 1 is just e. Remember, e is a number just like pi. Oh, happy almost Pi Day. March 14th, tomorrow is Pi Day, right? 3.14. So happy Pi Day, sort of. We'll call it pi, a bad approximation of Pi Day, because 3.14 is an approximation of pi. 3.13 is a bad approximation of pi. Happy bad approximation of Pi Day. So 2 plus x, right, that just kind of drops down, and that's from the rules of exponents and logs, how they're related. And so, right, because we know that e to the ln of x is just x, right, that's a fact. So we use all that stuff from earlier in this section. Ditch that. So that's how we're gonna have to solve for x if we've got it inside a log, right, is raising it to the power of the base of that log. So now we can just solve for x, and so x becomes e minus 2. E minus 2 on your calculator, you should have an e button, right? Minus 2, I get x is roughly 0.7182818. I lost track. 7182818.285. Your exact answer, though, even though it doesn't look very good, your exact answer is e minus 2. So here, this is your exact answer. And this is your approximate answer. Let's do let's do 62. 62. We have log base 2, right? So not log base e anymore. We've got log base 2 of x squared minus x minus 2 equals 2. Okay. I've isolated my log. That's our first step. Now I'm going to raise it with a base of 2, right? Because I'm using log base 2. That's the only way that I'll get these things to cancel. And so what I'll do is I'll raise 2 to the power of log base 2 of x squared minus x minus 2 is 2 to the power of 2. Right? I have to do it to both sides. Confusing because we've got a 2 in a couple of spots. But how logs behave, right, is that these 2 cancels, and so the x squared minus x minus 2 drops down, and 2 squared is just 4. Bless you. There it came. So we've got x squared minus x minus 2. If I want to solve for x, right, this is a quadratic equation, so I can use the quadratic formula as long as I've got 0 on the right-hand side, which I can have if I just move the 4 over. So I get x squared minus x minus 2 minus 4 equals 0. So I get x squared minus x minus 6 equals 0. All right. Here I've got a equals 1, b equals negative 1. Oh, I don't know why I did equals there. Negative 1, and c equals negative 6. If you're able to factor this, right, that might be an easier option in this case. For me, I always like to just go with the same procedure, even if it might be a little bit longer, right? So here, what we get is x is negative b plus minus the square root of b squared minus 4ac over 2a. So I get x must be negative negative 1 plus minus negative 1 squared minus 4 times 1 times negative 6 over 2 times 1. So I get x must be 1 plus minus 1 minus 4 times negative 6. So I get 1 plus 24, so the square root of 25 divided by 2. So I get x must be 1 plus minus 5 divided by 2. So x must be 1 minus 5, putting me at negative 4 divided by 2, and 1 plus 5, so 6 divided by 2. So x is negative 2 and 3. One problem, right? Because if either of these x's yield a negative number inside the log, right, we can't take the log of a negative number, and we can't even take the log of 0, right? And so what we have, right, is, okay, we figured out we've got x squared minus x minus 2 inside the log, right? So another thing that, an added step that we need to know is that we need to make sure that x squared, is it plus x or minus x? Minus x minus 2 minus x minus 2 is greater than 0. So it can't even be 0, right? Since we can't take the log, since we can't take the log of a negative number, oops, that doesn't look like number, of a negative number or 0. Maybe it's nor 0, I don't know. I did math, English isn't my, might be nor, doesn't matter. right? And so we have to make sure that each of these are in the domain of the function, right? And so what we can do is we can just check to make sure. If we put in -2 squared minus -2 minus 2, well, I get 4 plus 2 minus 2. So I'm taking the log of 4. That looks okay to me. So therefore, x equals -2 is in the domain. What if we try 3 squared minus 3 minus 2, right? I get 9 minus 3 minus 2. I think I'm still okay, right? 6 minus 2. Yeah, which I guess it makes sense, but I hadn't thought that far because we forced it to be 4, I guess. Okay, no, that's good. Therefore, x equals 4 is in the domain. On a test, I would just want you to solve for x, right? So unless I ask you, make sure that everything's in the domain, right? You can just assume, because that's a whole other. So what we'll do on the test is we'll ask domain questions and ask you to solve questions. We're not going to do both, right? So we'll keep the domain questions separate, right? You will be asked to find domains of logs, right? That kind of thing. And so that's how we do it. But for us, we'll just, once you have this, right? X is -2 and x equals 3. Tap out, we're done. Okay. Let's do some of these word problems. 4.5. So we've got this compound interest problem. And in fact, we've looked at a couple of different interest formulas. So there's a thing called simple interest, which I'm not even sure we talked about, right? But simple interest is just, there's no compounding, right? For interest, we said, okay, sometimes the bank goes in and it compounds and it adds on whatever you've earned in interest to your principal amount. Simple interest, it just earns interest until you withdraw it. That's when you get your interest. There's also the continuously compounded interest, which I have a vague memory of talking about, where it's just always compounding, right? Not even every second, it's faster than that, right? But we looked and we compared at the yield of these interest rates, and they're not that different, right? And so we did some comparisons going back and forth, comparing interest rates and that kind of thing. So if we have these formulas, then we can solve some problems here. So let's see here. Let's do 89. A man invests $5,000 in an account that pays 8.5% interest per year, compounded quarterly. So we're going to find the amount after 3 years. So we can use the formulas, and because we're compounding quarterly, then our formula is going to be the amount after some time t is p, the initial amount, times 1 plus r over n. Remember, r is the interest rate as a decimal, n is the number of compoundings per year, right? That one's a little bit tricky. But if we're compounding quarterly, n is 4. Right? We've got 4 times per year. And to the power of n times t. So time is always in years, right? And so after 3 years, so part A, t equals 3, we know that, okay, well, 5,000, that 5,000, that's your principal amount. Right? And then your R is 0.085, right? Because that's your interest rate. N is 4 and T is 3. So we can find A of T is P times 1 plus R over N. Just writing it out so I can kind of fill it in as I go here. So A of T, the amount that I have after 3 years, that's what I'm solving for. So, and the P is 5,000 times 1 plus R was 0.085 over N, which is 4, to the power of 4 times 3, right? Time in years is 3. Solving these, we have to be careful, right? Because we have to first solve 0.085 divided by 4, add it to 1 to the power of 4 times 3, so to the power of 12, and then multiply it by 5,000. So you don't want to do it in the wrong order here. BEDMAS. 0.085 divided by 4 plus 1. Just checking in. 5,000 times 1.02125 to the power of 12. So now to the power of 12. So 5,000 times 1.28701863. Finally, times 5,000. We have 6435.093165. Which, if we're talking about money, right, we want to round to 2 decimal places. So 6435.09. That's how much we would have after 3 years. Part B, how long will it take for the investment to double? Okay. So now, right, to double from 5,000, I would want the amount to be 10,000, right? Because that's the double. And so what I'm going to do is I'm going to let A of T be 10,000. Right. So now, and just jotting down the general formula so that I have it here. A of T is P times, oops, 1 plus R over N to the power of N times T. We want to solve for T, right? Because we want to know how long is this going to take. And this is where we kind of got stuck last time, or when we first started talking about these things, right? Okay, what if we want to solve for time? And I got so excited that I wasn't even thinking that we would need logs and we didn't have them yet. So we kind of parking lotted that question, which we'll come back to now and just kind of solve. But let's see here. We're forcing A of T to be 10,000. P is still 5,000. In fact, if you wanted to solve this for any type of problem, right, you could use P here and then just do 2P over here, right, and just use any kind of P. What you'll find is that they'll cancel anyway, so it doesn't matter. And that's where that log of 2 divided by the rate comes from, the doubling time, the approximate doubling time. So, okay. We've got times 1 plus 0.085 divided by 4 to the power of 4 times T. We're solving for T. T is in the power. We know what to do, right? If we've got this exponential function, I first have to isolate the exponential, right? And so I'm going to work away inside those brackets, but also I have to kind of start clearing off some of this stuff, right? So the 5,000 can get moved over to the left-hand side. And so I've got 10,000 divided by 5,000 is, and I'll even do the 0.085 divided by 4 plus 1 in the same go. So 0.085 divided by 4 plus 1, I've got 1.02125 to the power of 4t, not 40, 4t. So I get 2 is 1.02125 to the power of 4t. I've isolated the exponential, right? Even though it has a weird base, we can still work with that. So I'm going to take the natural log of both sides. So I get the natural log of 2 is the natural log of 1.02125 to the power of 4t. Even as you get more comfortable, if you wanted to write with 4t down in front right away, that's fine, right? I just want to show you that we did do this, and the next step is to bring it down. But if you're feeling comfortable with the logs, then just bring it down in front right away. So then we've got the natural log of 2 is 4 times t times the natural log of 1.02125. Solving for t now, right? I can bring the 4 times the log of 1.02125 over. And so I've got t, and remember I like to have my solving for on the left-hand side, but natural log of 2 divided by 4 times the natural log of 1.02125. That would be your exact answer, right? And it is exact because this is the exact number, right? There are no more kind of hidden numbers, so we're still safe that way. This here is the exact number. That's hard to tell someone, oh, easy, after the log of 2 over 4 times the log of 1.02125 years, your investment will have doubled. That's tough, right? And so we need that decimal approximation. So the natural log of 2 divided by, and then in brackets 4 times the natural log of 1.02125. I get 8.2410. 12465.
Would we want to present that as like 8.25 years, or would that be supposed to be?
You could. Usually I would just say round to 2 decimal places or something. So then we don't have to spend time thinking about, you know, how much is a quarter of a year or 0.24 of a year, right? We'll just use decimals. Nice. 8 years and 3 months, I guess, ish. If February is one of them, maybe. Right, and so, all right. So we've got these tools, solving logs, solving exponentials. Let me see if I can find, when did we start doing logs and exponentials? Oh, here. So this is from, oh, whoops, March 6th. And we were talking about that population problem. Still very apropos. We've got this V of T, an infectious disease begins to spread in a small city, right? We were looking at that one. And now, if we wanted to solve for T, which is kind of the problem that we developed on our own here. So if we want to know approximately how long it'll take to reach 2,000 people infected. What we can do is figure out how long it takes to reach, because we decided that 2,000 was the horizontal asymptote, so it'll never actually reach 2,000, but we can still solve for t, right? And so if we pick a value close to 2,000, because we know it's going to get close to 2,000, but not get there. So what we had was this equation, and I'll just copy this. From March we had this, right? So what we said was, okay, we'll take something close to 2,000, close to 2,000. You could probably move it closer if you wanted to, but nah. So now, how long will it take for 1,950 people to be infected? Right, that's what we're solving here. So now, right, I've got t, just one t in here, but it's way down here in the denominator. So I do need to do a lot of work to isolate the exponential. But once I've done that, we know how to deal with that, right? And so let's get to work. So we need to isolate the exponential. So we've got 1950 is 10,000 over 5 plus 1245 e to the negative 0.97 t. To try to get e to the negative 0.97 t on its own, I'm going to move that whole denominator, I'm going to cross multiply it over to the other side. And so what I'm going to do is I'm going to have 1950 times 5 plus 1245 e to the negative 0.97 t equals 10,000. But now I'm back to that scenario that we had earlier, right, where I'm not going to expand this 1950 in, right? I'm just going to shift it over here because I'm trying to get this thing on its own, right? And so I'm going to divide both sides by 1950, so I get 5 plus 1245 e to the negative 0.97 t is 10,000 divided by 1950. I'll see if I get a nice number. I probably won't. I don't. What I would prefer to do, unless I get a nice number, then I'll simplify it. But because I get 5.128205128, I'm going to keep it as 10,000 over 1950, right? To get as an exact answer, or as much of an exact answer as I can. Now I can go and I can subtract 5 from both sides, right? Just slowly picking away and moving things over to the other side. So I get 1245 e to the negative 0.97 t is 10,000 divided by 1,950 minus 5. Divide both sides by 1245. So I get e to the negative 0.97 t is 10,1950, then minus 5, all divided by 1245. So it becomes this kind of big, nasty thing. But that's a number that we can deal with, right? It's just big. Okay. But now I've isolated the exponential. Now I can take the natural log of both sides. So what I want to do is I want to take the natural log of this whole huge thing on the right-hand side. So now take the ln of both sides. So I take the natural log of e to the negative 0.97t is the natural log of this huge thing. So I've got 10,000 over 1950 minus 5 divided by 1245. The negative 0.97t I can bring out front, but also the natural log of e is just 1, right? So that's nice. So this side, the left-hand side is really easy to deal with. So we get negative 0.97t times the natural log of e, remembering that this is just equal to 1. Which is, oh, I have to write that all out again. All right. The natural log of, I'll put them all up here, 10,000 divided by 1950 minus 5 divided by 1245. Solving for t, all I have to do is divide both sides by negative 0.97, right? Because the natural log of e is just 1, goes away. And so t is the natural log of 10,000 divided by 1950 minus 5 divided by 1245, all divided by negative 0.97. That's your exact answer. Gross, right? But in order to get your exact answer, right, you want to keep everything that doesn't boil down to a nice number, right? And so sometimes it's going to end up looking like this. And so here, I'll put it on this side. This is your exact answer or exact number. Now we can do the approximation. So if we do 10,000 divided by 1950, then minus 5, then divided by 1245, then take the natural log of that, then divide by negative 0.97, and it is just easier if you just do it all in your calculator. Make sure that you follow the rules of BEDMAS, right? And then what I get is 9.464 963,446. Can't remember if it was days or weeks or whatever for that problem, but it doesn't matter. Did I do it wrong, Chloe?
I think I've done something.
I got the same.
As me? Cool. Yeah, so you have to start at the 10,000 divided by 1950, then minus 5, then divide by 1245, then take the natural log of that, then divide by negative 0.97. So it's this kind of blooming outwards. Okay. Any questions about, yay, nice. About all that? All right. I think we're pretty solid on logs and exponents, right? We did spend a day and a half more than we planned on spending on it, but I think it's worthwhile, right? And so, but now what we want to do is we want to start moving into trig. So for the rest of the course, we're going to be working on trig. So trigonometric functions, sine, cosine, SOHCAHTOA, that type of stuff, right? And so start a new page here. Chapters 5 and 6. Doing sections together. Right, so section 5.1 and 6.1, because it's just, there's two ways of doing trig, right? We could use the unit circle, or we could use just special triangles. So we're going to look at both. As long as you pick one of the ways to memorize, because regardless, we're going to have to memorize some stuff. Just memorize one of the ways, know how to use one of the ways, and then we'll be good. All right, so it doesn't matter which one you use. I'll try to do a combination of both, and I know that's can be confusing. But 5.1 and 6.1 introduce two ways of solving trigonometric functions. The first one, we're going to be talking about using the unit circle. And then the second way is using special triangles. Which we won't actually, I guess, see the special triangles until 5.2, 6.2, yeah. But that's okay. We'll kind of know that they're going to happen. As a side note, as long as we are comfortable using one of these ways, right, then you'll be able to solve these problems. So as long as you are comfortable solving problems using one of these methods, I'm happy. I'll see. So as long as you're comfortable working with one of these, right, then that's all I need, right? You just need to be able to solve these things. No one's going to ask you, hey, did you use special triangles or did you use the unit circle here? Doesn't matter how you arrived at it. Right? I know that doesn't probably mean anything right now, unless you've done some, probably done some trig, right? If I say SOHCAHTOA, do you guys know what I mean? Sine is opposite over hypotenuse. Cos is adjacent over hypotenuse, that kind of thing. So that's what we'll be working on a little bit in these next few sections. So the idea is for test 2 to cover up to the end of chapter 6, but we're only doing 5.1, 6.1, 5.2, 6.2, and then 5.3, 6.4. Right, and so this is all we're covering the handout here until test 2. I might actually have to move over here, plug it in, just hiding. Oops. Weird. Guys. I know, poor planning. Well, I meant to charge it, but then forgot. Yeah, poor execution. It was well planned, but poor execution. Either way, it's my bad. All right. So, wow. So weird. Okay. So first, oh yeah. So up until test 2, we're supposed to cover the handout that you just got, right? And so if we can do that, like I said, for the final exam, there's only 1.5 questions that we won't have seen on a test, right? And so that's really nice. And so what Jen and I were talking about the other day was for chapter 7, we're just going to do what you need, and then we'll spend the rest of the time reviewing, right? Assuming everything is hunky-dory, whatever. But so the first 2 pages basically just introduce some notation that we need and just some terminology that we need. And so let's just talk about, well, let's talk about the unit circle, for example. The unit circle. And I don't know why, but the screenshots that Jenna took are all, I'm finding a lot fuzzier, like they're harder to read. I don't know. So I'll try to clarify some of the things if it's not, clear on the handout. So the unit circle is a circle with a radius of 1. It does assume that you know what the radius of a circle is. Or actually, I should use the tools that this program has, make a perfect circle. Will I be able to find the center? Probably not. Somewhere here, how about? Right. And so here, this length is the radius r. The equation of any circle is x squared plus y squared equals r squared. So any circle with radius r. The unit circle just says, okay, we've got a radius of 1. 1 squared is just 1. So then we have x squared plus y squared is 5. So then, what we do, because we're going to start talking, trig is all about angles, but also sine and cosine and all that fun stuff. But it is all about angles. So we need to be able to talk about just angles to start. And so what we do is if we have some circle here, like so, if we put it on an XY axis, like this, right, centered at 0. So if we place the unit circle on an XY axis, sometimes we write just XY as one thing, on an XY axis, right, centered at 0, 0, right, so centered at the origin, 1, 0 is way bigger than the other, there. Then what we do is all our angle measurements will start from the positive x-axis, right? And so what we say is we call this point our standard position, right? And so at this point, we're at standard position. And then from here, if we've got a positive angle, then we're moving counterclockwise. We've got a negative angle, then we're moving down this way. So here, this here is standard position. Just confirm, yeah. And if an angle is in standard position, we'll have what we call an initial side. Because if we think about an angle, right, here, there's an angle there, right? So what we've got is we've got this initial side here, and then we call this the terminal side, right? It started here and then it terminated here, so it ended here. So we're going to have an initial side and a terminal side. So we've got this initial side, and this is called the terminal side. Just for some terminology here. The point where it finishes, right here, let's say, is called the terminal point, right? And if we're on a circle, then, right, that's going to be on the circumference of the circle. And so this here is the terminal point. Should have made that triangle bigger, but it's okay. Didn't realize I'd use it so much. Okay. So what we have, right, is we're going to have some angle, right, that's determined by starting at this standard position, right? So here's our initial side, and then we move across here, right, to maybe this point here. Then I've got my terminal side, but also my terminal point is the point on the circle. So I've got the length of the side here, which is just 1, right, because we're working on the unit circle where the radius is 1. So if I'm starting here from the origin, right, on the unit circle, my terminal side always has the length 1, right? And then I'm moving my point all the way around here. You guys heard radians, degrees? You worked with radians and degrees. You see concept? A little bit? Yeah. Not really? No. So anyways, usually if we talk about degrees, right, if I ask you how many degrees is it from this side to this side, right, we kind of know it's 180 degrees, right? 360, even from here to here, we know it's 90, right? And so we've got that kind of fluency with degrees that we don't have with radians, but that we need to have with radians, right? And so for math, we use radians for trig functions. I'm pretty sure that the only field that uses degrees is going to be physics, because it's hard to measure something in radians. So physics will still use, 180 degrees, 360 degrees. They assume that you know radians because it just assumes that. But just as we know that, okay, we've got 360 degrees if we had an angle that went from here all the way around, right? What we need is we need to know what that is in radians, right, to be able to work back and forth. And so, let's see here. We know that an angle that starts in standard position with a terminal side at the standard position. Right, just trying to get used to all this terminology. If we've got here, that's our standard position. And then assume that we've got a positive angle. That angle goes all the way around here. This we know is 360 degrees. Right? Same thing with 180 degrees. If we start in the standard position and then we move halfway through, right, we know that this is 180 degrees. We know that, actually, let's just do a different color on the same graph here. If I go from here to here, I'm at negative 90 degrees. I'm not sure I wrote that down. I think I forgot to write it down. So let's write it down now. Angles moving clockwise, right, will be negative angles, right? So if you're moving in the negative direction, you're moving down and clockwise. So angles that are negative move clockwise, right? Whereas positive angles move counterclockwise, right? Start and kind of move the way that we think angles move, right, this way. So just like we have this kind of fluency, right? And even if I asked you, okay, where's 45 degrees, half of 90 degrees? Well, that's halfway through, right? So we've got these check-in points, right? We need to develop this fluency that we have with degrees in radians. And so we need to become as fluent in radians as we are in degrees. So what is a radian? A radian is going to be the length of that arc that we call it subtends the angle. Okay? And so here, I'll bring it in from your notes. This one here, actually, I'll bring in the whole graph too. How about all of it? There. So here, we say that, okay, if I start in standard position and I move to some point P, right, then in here I've got some angle. Right? And, you know, kind of doesn't really look like 45 degrees, so we wouldn't even really know what this is in degrees quite yet. But by definition, the number of radians that's at this angle is the length from here to here, which is weird to think about, right? But so we've got this length, and that's the angle that's inside there. Oops. So starting from, oops.
What's the length between the standard point and the terminal point?
Yes. So from here to here, right, this length is equal to t. So this is the length from standard position to the terminal point. That's going to be how many radians that angle is. So that's a weird concept to translate the length of that into the angle. But kind of works out, right? Because what happens is we know that the radius, or sorry, the circumference of a circle, right? If we think back to our formulas or Google it or whatever, right? The circumference of the circle is 2 pi r, right? And so we know that if we went all the way around, which would be the same as 360 degrees, right? Then we would have gone 2 pi r distance around here. On the unit circle, r is 1, right? And so what we say is if we're going all the way around here, we're going 2 pi radians. So the circumference of a circle is C equals 2 pi r. On the unit circle, r is 1. On the unit circle, r is 1. So C is just going to be 2 pi. So the angle of one revolution in terms of radians is going to be just 2 pi. The angle of one revolution in radians will be 2 pi, right? And just to clarify, that's the length of the angle, or the length of the arc, right, that you've traveled. The length of the arc that we've traveled. In one revolution. So if we break up our circle, right, there's some touchdown points that we can figure out. So if we've got this circle here, this unit circle, let's center it, I don't know, here. I'll map my standard position, because that's where I'm assuming that I'm starting all the time, right? I'll always start in standard position. So I can always draw that line from the center. So if we know that this distance moving counterclockwise is 2 pi, I can break this up a little bit. It's hard to work with pi, right? But we have to. So if I break this up and I talk about this distance, well, if I have 2 of those in a circle, then that distance must just be pi radians. Pi radians. I'll even say 2 pi radians down here. You can abbreviate it rad, radians. In fact, a lot of people have trouble knowing when to use radians and when to use degrees. And there's a setting on your calculator that you'll want to be familiar with, because you can switch from radian and degree mode. So I'll show you how to do that once we're into that, but into using our calculator. But if it's in degrees, it will say degrees. It'll have a little degree symbol. If there's no symbol, it's in radians, right? And so that's on your handout. But I'll just go grab it here. The little note. So the note says, when an angle is given without stating whether it's in degrees or radians, we assume that it's in radians. Okay, and radians we can abbreviate. We can also write just rad, right, if you want. But it actually doesn't have any units, so we use that because we have a hard time without units. But if you want to write rad or no units, that's fine too. What if we break this up even more, right? What if we break it up into quarters, just like we did? So we went 360, 180, we know 90, right? And just so we have this kind of equivalent trade between radians and degrees. So then if we're talking about this angle, that's going to be pi divided by 2, right? So here we've got pi over 2 radians. Okay. What you'll see on your handout, and what we just simply have to memorize, and it's not that fun, but we just have to memorize it, is this table 1 and the unit circle. Let's see if I can blow it up here. Little blurry. Okay. So, there are 3 other points we will need to memorize. So here they are. Just these 3 points should get you by, right? And so what happens if we're on the unit circle and we're starting here, if I go a distance of pi over 6, then this angle between here and this point, right, is pi over 6 radians, pi over 4, and pi over 3. So we'll look at how to develop these points, because now, right, if we think about, okay, well, here my x value is root 3 over 2. So if I drop down, my x value here is root 3 over 2, and then my y value is 1 over 2. So I've got these special triangles in there, but at the end of the day, if you don't want to rely on special triangles, because that's another thing you have to memorize, you could just memorize these points, right? And so here, these are just points that we have to memorize. So when the angle is pi over 4, for example, x is root 2 over 2 and y is root 2 over 2. And so, for example, when the angle is pi over 4, we know x is root 2 over 2 and y is root 2 over 2, right? Because they're the same, yeah. And because it's kind of hard to see, how about we just write these out? So memorize. I don't love to get you to memorize stuff, but it's just what we got to do. And it's going to make our life so much easier. If we've got our terminal point, or terminal, oh, whoops. You know what? I'm not even going to call it terminal. I'm going to call it just the angle. If we've got an angle of 0 radians, pi over 6 radians, pi over 4 radians, pi over 3 radians, and pi over 2 radians. Yeah. Squeeze it onto the same page here. And so now I'm talking about the terminal point xy from this table, and we're just writing out the table. If you're moving 0 radians, your angle is 0, so then you're at 1, 0, right? X is 1 and y is 0. If you've moved pi over 6 radians, then your x is root 3 over 2 and your y is 1 over 2. We did pi over 4, so let's just do root 2 over 2 and root 2 over 2. And when we've got pi over 3 radians, then x is at 1/2 and y is at root 3 over 2. And when we're at pi over 2, remember that's the equivalent of 90 degrees if you want to make that link, right? 90 degrees, x is 0 and y is 1. And so then we're at 0, 1. So let's go do some of these examples, see what we've got, what types of problems we're looking at. Find the terminal point, right? And so here, these points are the ones that we've got, right? And so what we want to do is we want to find the terminal point on the unit circle determined by the given value of t. So if we do, let's do 24 first, just to get into the group. So if t is -3 pi, right, the negative just tells me that I'm moving clockwise, right? Moving down. So clockwise. And what we can do is we can just draw a circle and try to figure out what this thing looks like, right? And so if I'm moving clockwise, then if I move here all the way around, then I know I've moved -2 pi, right? So to this point, I'm moving -2 pi. But I want -3 pi. So after this, what I can do is I can keep going, right? Another pi. Just making sure that I go another pi, which is on this x-axis, right? And so here, if I go from here, right, this would be -3 pi, that distance. If I'm on the unit circle and we want to find this terminal point, right, I know my radius is 1, my origin, well, my center of my circle is at the origin, 0, 0. So I know I've moved out -1 in the x direction, but 0 in the y direction, right? So here I'm at -1, 0. So that's the terminal point, right, is at -1, 0. So this is your terminal point equals -1, 0. Kind of off, but So what if we do 26? If t is 5 pi over 2, let's just kind of think about this as, okay, well, I'm using 2 pi and pi over 2 as reference points, right? And so I've got 5 over 2, which is 2.5, right? So again, the same idea. What I'm going to do is, but now I'm moving in the positive direction. I'll make a bigger circle here. Positive direction. If I move from here to here, right, I've moved 2 pi. Right? If I want to move another half a pi, how appropriate that we're so close to pi day. Pi, pi, pi. So then from 2.5, or so from 2 pi, sorry, I need to move an additional half a pi. So here I'm at 2.5 pi, right, which is 5 over 2 pi. What? Everything's got a low battery. So our terminal point, right? So here's my initial side here. Here's my terminal side, right? Not that far from my initial side. It's just looping around and around and around and around, right? And so we want to go to here. Our terminal point is when x is 0, right, and y is 1. So this is at, so our terminal point here, our terminal point is 0, 1. What if we do, well, let's just have a look at, just so we know how we're going to use this table, right? Why do we need to memorize this? These two we don't really, right? Because they're kind of obvious when we look at our circle. But these ones are going to be less obvious. So we ended up at pi over 2 radians. That was ultimately our distance from the initial side, right? And so pi over 2 was at 0, 1, which we just set. And so that was our terminal point. So let's have a look and see if we get into some of these other ones. Let's look at the next couple of problems here. For this one, I'm kind of introducing the concept as we go. But what we do, I've already said it, right? We use this reference angle, right? Because we just end up using the shortest angle, pi over 2, to figure out what our terminal point is, right? So even if we loop around and around and around and around, if I end up at pi over 6 here, then the distance here would be my reference angle. What we can do is we can even do that in other quadrants, right? But it means that we have to figure out what these quadrants are. So I guess before we can do this, let's just see here. Who wants to be on that page, does it? How about this? So we need to use reference angles, right? We need to use reference angles in order to use the information that we've memorized in the table. In order to use the information we have memorized. And so what we do is the reference angle, it's just going to be the distance from the x axis. So the reference angle is the distance from the closest x-axis. So if we think about our xy axis here, I guess I should make it a little bit longer, make it even, like that. Well, we've got our first quadrant. So what we do is we start, and that's why we use that as our initial side too. So we start in the first quadrant, and then if we're moving counterclockwise, we're moving through the second quadrant. Third quadrant. And then the fourth quadrant. In the first quadrant, x is positive and y is positive. In the second quadrant, x is negative, but y is positive. In the third quadrant, x is negative, y is negative, right? So here we got negative, negative. And here we've got x is positive, y is negative, x is positive, negative. So it just depends on if these values, so remember the ones that we memorized, right? If you've got pi over 6, right, but you're over in the second quadrant, so you've moved all the way over here, right, and now this distance is pi over 6, then your x must be negative, so then your x must be negative root 3 over 2, right, because you're in that second quadrant, but your y is positive, so your y would be positive 1/2. So the signs of these x's and y's are going to depend on which quadrant you're in. And so here, you've got positive x and positive y is how I'll denote it. Right? xy. Usual notation. So if we move around here, we've got a negative x, positive y. Negative x, negative y, and then positive x, negative y. So the reference angle is the distance from the closest x-axis. Right? And so I guess we can do some of these by example. Let's do 41. Right? And the problems. Wait. 41. We've got t is 11 pi over 6. So it's positive, so I know I'm moving counterclockwise. And what I want to figure out is, well, I know that if I push this to 12 pi over t, 12 over 6 would be 2, right? So I know I'm going to be pretty close. Okay, what a terrible circle. I'm going to be pretty close to almost all the way around. Right? In fact, I only would need to move pi over 6, right? Another 1 pi over 6 to get to that full distance. And so what we need to do is, I'll even clean up this circle. What a bad circle. There we go. So if we've got our standard position here, and so we're starting and we go around to here, let's say, well, maybe we go a little bit further. (11π/6) is that distance. Keeping in mind, right, all your check-in points, if I was able to go 2 pi, I would have ended up back at the standard position, right? And so the angle that I've got in here must be another π/6, right? And it doesn't actually matter which way you go, right? If you keep going or if you go down, technically from standard position, your reference angle is moving down (-π/6). But that means you can't really add your angles. And we ignore the negative anyways, because we don't have a table for the negative values. But this would be your reference angle, right? So here's your original angle, 11π/6. Your reference angle is going to be the shortest distance from the x-axis. So your reference angle now is π/6. So if we've got a reference angle of π/6, right? Well, from our table that we will have memorized, π/6 gives me an x value of √3/2 and a y value of 1/2, right? So if the reference angle is π/6, oops, π/6, then x is √3/2 and y is 1/2. Now we need to keep track of, okay, well, I'm actually in that fourth quadrant, so x is going to be positive, but my y is actually negative. So here, the point that we're interested in finding is this point, right? And so we'll call that our terminal point T. Find the reference number. Maybe we shouldn't call it T, maybe we should call it P for just a point, right? Since P is in the fourth quadrant, x is positive and y is negative. Right? So what we can say is that P is, and I'll use bigger brackets here, √3/2, that's a positive x value, but negative 1/2 for your y. Right? So what we do is we say, okay, well, as long as I know how this first quadrant behaves, and then I keep track of positives and negatives in the rest of the quadrants, they'll behave the same way, right? As long as we're thinking about the distance from the closest x-axis. Uh-oh. We're out of time. Time flies when you're having fun. Okay. Low battery everywhere. Okay. Whatever. So I want you to go through and try the rest of those problems, right? Because we will need to practice this stuff. It's all new. And in my opinion, not quite as fun as exponents and logs. So it's a little bit harder to wrap our heads around. So definitely try to practice those. And I'll just keep you guys updated. If I send you email, did you guys get that email that I sent at the beginning of reading break? That one went through fine and everything? Cool. Because that's how I'll contact you. I won't go through Moodle because it's hard to, sometimes Moodle sucks, so. But if you've never gotten an email from me, should check that out. Make sure that you can get an email from me. All right. Have a good weekend, guys. See you later.